So basically, I'll just start from the beginning. So project option number 2, you're tasked with implementing AI that's playing a 2-player game. So you have 2 players, basically in an adversarial game. One is playing against the other, and each player is trying to win the game. So there's some sort of goal that they're both trying to reach. So player 1 is trying to make the best move possible for themselves, while at the same time limiting the advantage of the possible moves for player 2, and player 2 is doing the opposite. So everyone's trying to make the best moves and make sure they don't give away the goal to the other player. Okay, so you have an initial state of the board where you have a starting position, you have successor states whereby I'm going to make a move. Obviously, that's going to change what the board is. You're going to make a move. That's going to change what the board is, so on and so forth. So there's some set of valid moves for each board configuration, and you as a programmer could figure out a function that would evaluate that. So in tic-tac-toe, you can go anywhere in the board. You can either put an X or an O wherever you want. Obviously, you're trying to get 3 in a row, but you can move wherever you want. In Othello, there's only certain spots where you can go. You can only go to a spot that's adjacent to another piece. You can't go straight to a corner or a side. In chess, each one of the pieces has certain movements. Some of them are blocked. You can't move pieces through other pieces unless they're allowed to do that. Sometimes you can't move a piece because it'll put you in check, so on and so forth. So there are rules that you can use to figure out, from your current position, current board state, what other board states there are. So in addition to that, you can also do tests on the board to figure out if the game is won. So in the game of chess, it's if you checkmated the opponent, they can't do anything to block your check. In tic-tac-toe, it's somebody's got 3 in a row, so on and so forth. And then another term I'll define is a utility function, which gives basically a heuristic numerical outcome for the game. So this is a numeric approximation of how good that current state is. So in the case of Othello, something good might be I have more pieces than my player. In chess, it may be the total point value for all my pieces is greater than my opponent. I've taken out his queen and his rook, so technically I have an advantage. Tic-tac-toe, it could be which pieces you have. Maybe the center piece is more valuable, or the corner pieces are more valuable. And so by using these, you can basically graph out all the different possible moves that you have at your fingertips. So you can imagine, here's my initial state. Here's if I move to position 1, position 2, and position 3. Here's what would happen when my opponent goes. He can make these different moves off of those different moves. And so if you were to build this entire tree down for all possible moves, you could solve the game perfectly. You could say, oh, it's my starting move. If I make this move and then my opponent makes that move, I should make this move next and that move, and figure out what is the optimal solution for the game. For simple games like tic-tac-toe, this is really easy. I mean, tic-tac-toe, I think, only has like 5 moves. 4 moves for one player, 5 moves for the other player, and then the game's over. So it's only a 9 deep tree. Chess is like thousands of moves deep, and it could go much further. And Othello, once again, same thing. So it's really computationally expensive to build this whole tree. Now maybe you could do it ahead of time and then bring it with you. Maybe have like a supercomputer chug on it for a long time, figure out what's the optimal game that it wants to play. But in real-time games, you wouldn't be able to do that. Okay. So you can see this example for tic-tac-toe. So starting board is completely empty. First player goes X, they get to choose anywhere on the board. So there's 9 different possible spots they can go. Next player, they get to go their O, they only have 8 more choices of where to go, so on and so forth. And you can figure out that, what the terminal cases are. So what are the points at which the game actually ends? So, O got 3 in a row, this is a draw, this one X got 3 in a row, so on and so forth. And so this can be used just as a general case for any adversarial game. And the algorithm that we use to approach these problems is called the min-max algorithm. So based upon the current player that the AI is representing, just like I was saying, they're going to try and make the moves that are the most advantageous to them, whereas the opponent will try and make the move that's most advantageous to them. So as X, I'm going to try and make the move that, or sorry, I'm going to assume the opponent is X. As X, the opponent will make the best possible move that it can make, which is, of course, the worst possible move that I could make. So we're going to try and find the minimum possible state for that. So if we have a utility function that gives us a numeric outcome for each one of these states, based on its child states, this would probably be the worst, or would be the worst for me, because it's the best for my opponent. Same, when it's my turn, I'm going to look for the best possible state. So you do a max, hence the min-max. So you're looking for the minimum for your opponent, the maximum for you. Minimum for your opponent, the maximum for you. So on and so forth until you actually get all the way down to the bottom. And so that's basically what we're saying right here. How do you do this? Realistically, you're doing a depth-first search. So you're going all the way down to the bottom of the tree, figuring out what the value of this is. So in this case, they won. This case, we tied. In that case, I won. So I would want this one. And then going back up the tree, you would figure out, you would basically assign these values to the different states. So what you'll eventually get is, this is more positive than a different move that I might make. And you would want to make the maximum move along the leg. Okay, good enough. So just another example of that same sort of thing. So in this case, you can see we got our utility function here. And so let's say I'm moving first, so that's the maximum. Then my opponent is going, and these are the actual utility functions at the bottom. So out of all these possible states, each parent node will get one value assigned to it, depending on whether it's a max level or a min level, because either it's my turn or it's my opponent's turn. It's going to evaluate each of the children and choose whichever one makes the most sense, and choose whichever one is numerically the optimal solution. So for min, my opponent's going. So it's obviously going to choose the one that's the best for me, which is the worst for me. So it's going to choose the lowest number in each of these possible states. So this parent state has 3 children, 3, 12, 8. Opponent makes the best move it can, or would make the best move it could for this. So it choose 3, same 2, 2. Now it's my turn. Based on what my opponent would have done, I would have chosen the best one, so 3. So at best, if I assume my opponent is going to play the game as best as they can, this is the state we're going to wind up in. Now, obviously, if one of these is AI and the other one is a human player, that may change. I may make the best move, and then the player makes a mistake and chooses the wrong one. Now we're in a state that's actually better for me because the opponent didn't do quite the right move that it should have, the optimal move that it should have. And so this is kind of just working its way through that. So for each operator, so for each child, or sorry, not each child, but each possible move, basically do the min-max algorithm for each of them. Depending on which level it is, you're either doing min or max. And it's recursive, so you're going back down through each level. So, if you get to the terminal state, actually just return the number, the numerical value for it. If you're max and you get to a state that's greater than your current max, choose that one. If you're in the lowest, you choose the lowest. I'm sorry, if you're in min, you're going to choose the lowest. Okay. So an optimization for this is keeping track of the current best value that you've come across while you're traversing the tree. So since it's a depth-first search, and you're populating these numbers back up the tree, so in this case, right, I've already gone down from this parent node down to this